Hi everyone. It's been a while since I've made an update on Steam Revolution. There has been some progress, but it's been somewhat slow, and admittedly having a baby has not made the progress any faster. I thought I'd try something a little different and make a video while I'm working on a feature rather than trying to make a video after the fact. I hope that'll make it easier to sort of collect the initial starting point, and maybe I'll be able to expand more on the reasoning of why I'm doing something and the steps that are involved in doing it. What I'd like to do is to improve the quality of terrain rendering. There's two reasons that I'd like to do this. The first is that I think I can improve the visual quality of the images that are rendered, and the second is that I think that I can also make it run a bit faster. There are two main ways that the quality of the image can be improved. The first is that if you look at the terrain sort of from the side at the edge, you can see underneath. And right now, you'll see sometimes the land underneath the water or the water underneath the land, and it doesn't look very good. It's a bit sloppy. Another thing that can look bad is if you zoom out, the rivers can start to fall apart. And this is happening because for most of the terrain, it's pretty flat and doesn't have major color contrasts, and so you can simplify it a lot without having big visual errors. But when you come to the transition from land to water, the errors become much more obvious. The rendering can also probably be made faster. You might ask, since the rendering is already fairly fast, why even bother? Well, there's a bit of pride in craftsmanship, but also I want the game to be able to run on lower-end hardware, on laptops, integrated graphics, and stuff like that without a problem. So let's talk about why I think that things can be made faster. Previously, I was using DirectX 11 instead of DirectX 12, and that guided some of my thinking. In DirectX 11, one of the issues that I had was that the driver overhead was actually really killing the CPU time. To avoid the overhead from draw calls, I switched my rendering system to draw the terrain tiles as instances of the same solid mesh, and it would just translate them to the correct position in the vertex shader and read from a height map to determine the vertex Z position. In this way, I have one draw call for all of the ground and one draw call for all of the water. The problem with reusing the mesh for each terrain patch is that the meshes have to be identical, and thus they need to cover the entire domain of the patch in the XY plane. However, DirectX 12 is fast enough that I think that I can go back to making an individual draw call per terrain patch and customize the mesh per patch. This will allow me to remove triangles that would otherwise be occluded because they're underneath, say, the water or underneath the ground. This can both reduce the number of triangles that are drawn and thus the amount of vertex shader work, and it can also reduce the amount of overdraw, which will make the rasterizer and the pixel shader do less work. The other thing that will let me do is to simplify more aggressively in places that don't need as much detail while retaining detail where I need it. Even when the same number of pixels are covered by a mesh, reducing the number of triangles can have a large effect on performance. There's the obvious way in which there's less vertex shader work, but less obviously, it can actually reduce the amount of pixel shader work by a pretty drastic margin. In order to numerically calculate derivatives for texture sampling, GPUs will actually render 4 pixels at a time, known as quads of pixels. At the edges of triangles, it will still render a quad even outside of the triangle boundary. And so, if you have lots of edges, you might potentially be drawing lots of pixels that are then not directly used, but are just used to calculate derivatives. This is a form of overshading that is less obvious than directly overlapping geometry. If you compare these two captures, The only difference is that in one of them, I draw the mesh at a normal resolution for the terrain, and in the other, I draw it at the lowest available resolution. What you can see is that with the high resolution mesh, it takes about 1.2 milliseconds to draw the terrain, and in the low resolution mesh, it takes just over half a millisecond to draw the terrain. Although I don't expect to get all the way down to half a millisecond, this is a proof of concept that shows that there's significant savings that could be had. The first step of this process was to convert from using instance draw calls to a whole bunch of individual draw calls. This is a necessary step for the whole plan to work, and is also the first chance that it might fail if it turns out that the CPU overhead from doing a bunch of draw calls is unacceptably high. This is also where I ran into my first stumbling block. The way that my instance draw calls worked was I had a buffer that contained the tile offsets, and then each instance would use the instance ID to read what its tile offset was. The draw indexed instance function actually takes as its last argument the start instance location, and my assumption was that I could just set that to the effective instance number and have the instance count be 1 and make a whole bunch of calls like that, and that would allow me to still use the same instance buffer and leave my shader code alone and just do a bunch of separate draw calls now. Unfortunately, the instance ID that was passed to the shader seemed to always be 0, and so I just got a whole bunch of copies of the first instance, and that didn't work. So instead of doing that, I decided to pass the per tile data through constant buffers where each draw call would have a different constant buffer. This is somewhat memory efficient because the minimum alignment of a constant buffer is 256 bytes, and I'm using that to just pass in a tile offset per instance, but it is what it is. I then ran into a self-inflicted problem where I thought the number of shader visible heap resources was limited to 2048, which turns out not to be true. I think I must have just gotten confused about the number of samplers that are available to a shader instead of general heaps that are available to the shader. But anyhow, I was operating under that assumption for a little while, and the problem is that constant buffers are stored in a heap visible to a shader, so I thought that I needed to do some sort of dicing up of my draw calls into a bunch of these somewhat small heaps. I sort of grumbled to myself about the inconvenience of this and started implementing it until I eventually realized that I was just wrong, and I then deleted that code. Having crossed those hurdles, I now had a working solution. To keep my timings comparable between versions, if I don't state otherwise, the times are the amount of time required to draw the view of Spain. Before my changes, it took 0.16 milliseconds to record the command buffer, and after my changes, it now takes 0.26 milliseconds to generate the command buffer with the additional draw calls. When zooming out, every tile now needs a draw call, and this increases the amount of time to generate the command buffer to 1.85 milliseconds. Unfortunately, I didn't think to record this time before making my change, so I don't know how much of this is from the removal of terrain instancing versus the time spent to render all of the trees and buildings. Regardless, the amount of time added by the terrain rendering can definitely be reduced by using some sort of a hierarchy where I have fewer draw calls for larger patches of terrain when I'm zoomed out. This isn't critical because I'm well below my 8 millisecond budget, and also the CPU time is less than the GPU time to render, but still, the more CPU time spent rendering, the less CPU time available to do simulation. So I'll put that on the to-do and may get around to it later. Speaking of GPU times, this is when I ran into another problem. My GPU's control panel wasn't working, and I needed it to work in order to record some video footage of the game, so I installed a new driver, and that fixed that. However, it turns out that installing the new driver broke my profile capturing software. After a bit of troubleshooting and debugging, I eventually just installed an older driver version, and that fixed the profile capturing. However, in the meantime, until I managed to fix that, I implemented my own timing mechanism within Steam Revolution using timestamp queries. In some ways, this is probably better because I can get more consistent timings by programmatically inserting these into the instruction stream and averaging over many different frames to get more statistical robustness than sort of using a single frame and hand drawing a selection box. So all of the times that I report in the future are going to be using this new timing mechanism, and we have a starting point now where I can say that 2.81 milliseconds are used to render the entire frame, and 1.15 milliseconds of that was used to render the terrain. At this point, I've converted to a bunch of individual draw calls, but I'm still using the exact same mesh for each one of the draw calls, so I'm effectively just doing really inefficient instancing. My next step, therefore, is to make unique meshes for each one of the different terrain tiles. This is the last main hurdle that I need to cross in terms of will this work at all or not, because it's possible that the amount of memory taken to represent the entire world's terrain at the same time is just going to be too much. I really don't want to implement some sort of complex system of streaming terrain data in, and so I need to make sure that I can have all of the data just stay resident all of the time. At this point, I'm just in the proof of concept stage of testing if this is going to be feasible. So I'm not worried about making a whole bunch of actually unique meshes. I just want to see what's the memory usage going to be. So I made a whole bunch of identical copies of meshes, but stored each mesh with its own unique set of vertices and indices. In my initial attempt at this, I was actually shocked because I have 8 gigabytes of system memory, and the memory usage in the game just shot past that to like 20 gigabytes. There were 2 obvious potential culprits to this memory usage. One of the problems is that it turns out that I was constructing my mesh in a builder, just some data structure where I was accumulating the positions and indices, and was not freeing that memory after uploading it to the GPU. The second problem was that maybe I was just storing way too much detail. If I'm going to have the whole thing resident, I can store really a lower resolution, and anyhow I'm going to eventually do some mesh simplification, so to get the same quality I don't need as many triangles. So I got rid of one of the MIP levels of my terrain. Unfortunately, neither of those was sufficient on its own, and my memory usage was still pretty bad, taking around 9 gigabytes or so, which is just too much. I knew that another potential source of inefficiency could be from the resource alignment requirements in DirectX 12. And in particular, looking up, I found that the alignment restriction is that any sort of buffer needs to have 64 kilobyte alignment. And any given mesh has both a vertex buffer and an index buffer, so the smallest size the mesh can take is 128 kilobytes. Especially for some of the lower resolution MIP levels, this is definitely overkill. In particular, my very lowest resolution, I have just 2 triangles per terrain patch, and that's 4 vertices and 6 triangle indices. In order to test this theory, I wrote some code that would measure the theoretical amount of memory that actually needed to be used by the meshes, and then the amount of memory that was actually occupied after applying the alignment restrictions. This gave a pretty clear picture. The total memory that theoretically would need to be used was only 210 megabytes. the index buffer accounted for 100 megabytes of that, and the vertex buffer for 110 megabytes. But the memory occupied after the alignment restrictions was 4.8 gigabytes. Even my highest resolution terrain tiles were only taking about a quarter of the 64 kilobytes, and so the memory overhead was just incredibly high. I'll briefly note here that previously I was using two 16-bit integers for the XY positions of the vertices, and in these measurements I am using three 32-bit floating point numbers for the positions. I changed the vertex representation in anticipation of my needing that in the future. At some point I'll need to replace reading the terrain height map in order to get the vertex Z position, because when I do terrain simplification, I'll need to ensure that the border between ground and water has no cracks. The problem is that the ground heights and the water heights are stored in different textures, so any slight inaccuracy in the position will cause there to be a slight difference in the Z positions. At the moment, I have overlapping triangles from the two different height maps, and the occlusion is resolved by the Z buffer, so there doesn't need to be this precise joining between the vertices, but it will become an issue later. In total, I was drawing 2 meshes per terrain tile times the number of MIP levels. 1 mesh for the water and 1 mesh for the ground. To avoid the alignment overhead, I now combine all of the meshes into one single mesh. In other words, all of the water meshes, all of the ground meshes for all of the different MIP levels and all of the tiles are stored in a single mesh, and then each tile, each MIP, each ground or water then stores an index offset and the number of indices that should be used. This combined mesh can have way more than 64,000 vertices, so I also had to increase the size of my indices from 16 bits to 32 bits. I also did a quick and dirty way of making the meshes unique per tile. If all of the vertices of a triangle are below the ground, or vice versa the water, then I will discard that triangle. Since this is just a quick test, I didn't bother actually removing the unreferenced vertices, so the vertex buffer usage is a little higher than it should be, but this is just really a test and proof of concept. Now the alignment restrictions are basically not a factor anymore, and the total amount of memory is 266 megabytes. 156 is from indices, and 109 megabytes are from the vertices. Because I've removed some of the occluded triangles, the GPU time is a bit better now. It now takes 2.66 milliseconds to render the entire frame, and the train is taking 1.01 milliseconds as opposed to 1.15 before. If we look at the edges of the terrain again, we can see that the culling is working as there's not as much of the mesh below other meshes. However, if you look closely, you can see that there's still a bit of overlap. It's not a perfectly clean join between the water and the ground. Previously, I had a single mesh, so all of the positions were relative to the tile, and then each individual tile was drawn with an offset that was added to the positions. Now that I have unique meshes, I can store the positions in absolute world coordinates, and this makes some things simpler. There are several benefits. One is that previously 256 bytes had to be used for every constant buffer. This is an alignment restriction that comes with DirectX 12. Honestly, this memory usage isn't a huge concern, but it's data that probably needs to be uploaded to the GPU for every draw. Much more importantly is that the amount of time spent on the CPU is significantly lower. This is basically because there's actually a fair bit of management that needs to be done to handle the descriptors in DirectX 12. My understanding is that basically you need to have 2 different heaps. You have one heap that stores the descriptors that you're creating, and this is not shader visible. And then you have a second heap that is shader visible, and the descriptors need to be copied into it. Once you've copied the descriptors into the shader visible heap, then you need to set the root descriptor table to point at those descriptors. This management overhead basically comes because I was setting a descriptor for every one of my draw calls. I need to have a constant buffer for the world transformation, and then I also need to have the tile offset. With absolute positions, though, I don't need the tile offset, and I can reuse the world transformation buffer between all of my different draw calls. Much less importantly, but there's a side benefit that the vertex shader becomes a little bit simpler because now I don't need to read from a height map texture because the heights are stored in the vertices themselves. I also took this opportunity to move some of the mesh selection logic that I was doing in the command buffer generation to earlier while I'm still waiting for the GPU. So this reduces the latency for actually generating the draw calls. I don't think I had explained before exactly what the difference between render prep and render command was. Render prep is the work that I can do to prepare the frame for rendering where I don't have to have the GPU available. And render command is when I actually generate the command buffers for the GPU, and I need to wait for a previous frame to finish in order for those command buffers to become available because I'm double buffering them. Anyhow, you can see the results of my change are that the amount of time to generate the commands has drastically reduced. It was previously 1.85 milliseconds to draw the zoomed out frame, and now it's down to 1.0 milliseconds. My next big change was to restructure how I'm generating the terrain mesh. Basically, the purpose of this is to lay the groundwork for how I'm going to generate the seamless mesh when I get around to doing that. Previously, the way that it worked was that I would generate a mesh per patch, and that consisted of maybe 16 or 32 vertices on the side, and I would generate all those vertices and then generate the triangle indices afterwards. By generating all of the vertices beforehand within a terrain patch and then indexing into them, this is a way of avoiding a lot of duplicate vertices, and the only duplication is going to be at the boundaries of the patches. However, in the future, when I'm generating the seamless mesh, I'm going to need to have more complicated logic that's going to operate on quads of vertices at a time. And I'm going to need to sometimes generate vertices along one of those quad edges, and that's going to make the indexing much more difficult and not so easy to just be like, oh, it's a grid coordinate this and that, and so that's what the triangle index needs to be. My solution is to keep track of the vertices that have been created or not with a table that's indexed by the ID of the vertex, which is given by the end coordinates of the vertices along the edge. I say vertices along the edge because in the future I'm going to potentially have vertices that are created along one of the edges to find the intersection between the terrain and the water. But this also needs to be generalized to work for the actual, terrain vertices that are at the integer grid coordinates. And so those are going to be indexed by just repeating the vertex ID. And so it's like an edge from a vertex to itself, effectively. The nomenclature gets a bit confusing here because I effectively have sort of like 3 different types of vertex IDs. But you start out with your vertices that are just the grid coordinates is their ID, right? That's the vertices of the terrain mesh. Then you have an ID of a vertex that lies along an edge, and that has 2 of those grid coordinate IDs. And then from that, you look up into a table and you get the index into the vertex buffer that is going to be referenced by the triangle. I can pack 2 32-bit source vertex indices into a 64-bit edge ID, and that's just done by using some bit shifting arithmetic, and then use that to index into a hash map that then returns my vertex buffer ID. At the moment, it's possible for vertices to have the same XY coordinate but a different height, depending on if they're part of the ground or the water. And that requires that I have 2 different hash maps for keeping track of the different vertex IDs, But eventually, once I get a seamless mesh, that won't be the case anymore. All vertices will have exactly the same height, and I will only need one hash map. With this change, I'm just restructuring how things work by generating effectively the same mesh. The benefit that I get out of this is that now I don't need to actually create any of the vertices that are unreferenced, and so the size of the vertex buffer reduces. It was previously taking 110 megabytes, and now it's taking about 60 megabytes. Over the course of writing this, I did a few optimizations that drastically improved the speed of generating the terrain mesh. My initial implementation took about 8.3 seconds. In my first pass, I did a bit of code cleanup, and I changed, instead of reading the height map multiple different times, per quad I would just read the height map once for each of the grid coordinates and then reuse those values. In particular, I was using those values both to set the z position of vertices and also to determine occlusion. This cleanup saved about 1.3 seconds. My next improvement is it turns out I was valuing the height map using a cubic B-spline, but this is not necessary. For generating the terrain, it's possible to just directly read the height values. As it turns out, I had already upsampled the height map using cubic B-splines at a 4x higher resolution, and so I could just directly read those results. Upon further investigation, I noticed that also in various other places, like in the simulation code, I was reading from this same height map, and again I was evaluating the cubic interpolation every time, and that's not really necessary. You need some sort of interpolation still, but a linear interpolant would be sufficient. With these changes, the generation time was down to 5.6 seconds, which is a significant improvement. I don't want to get into some rant about the standard library, but it was known to me beforehand that the implementation of hash maps in the standard library is trash tier. I wrote a custom special purpose hash map, and the time got down to 1.7 seconds. I had replaced the data structure, but was still using the standard hash function, and I decided to then replace that with the XX hash library, which provides better hashing, and that reduced the time further to about 1.4 seconds. If a custom hash map sounds scary, it's really not. The entire implementation fits on one page, and I'm showing it here. My go-to implementation is that I use linear probing and just ensure that I have enough space that I'm not going to exceed the capacity of the table. It's up to the calling code to allocate sufficient space, or else trying to find a key could result in an infinite loop. It's important to note maybe that the key and value are both pretty small, so I store them together, and the entry is 16 bytes, so that means that 4 entries will generally fit in a cache line. So the linear probing will typically read maybe 1 or 2 entries, probably not very often more than 4. This means that even though your accesses to the hash table are probably going to be scattered and not in cache, typically you're going to have one lookup into system memory to actually retrieve a value. I also ensured that the capacity is a power of 2 to allow me to wrap around the table by using a simple AND with a mask. Now that I've done all of that prep work, it's time to actually make a seamless mesh. Now, per quad, I need to generate the correct set of vertices and triangles for both the ground and the water. The first thing I do is I check all 4 vertices and I determine which one, if any, is a ground vertex. Conceptually, I will always consider the ground vertex to be vertex 0 if it exists. There are basically 4 cases to consider. The simplest is if there's no ground vertex, then the entire quad has to be water, so I just generate a single water polygon. If there is a ground vertex, there are basically 3 more cases to consider. It could be that there's no water, there could be 1 water polygon, or there could be 2 water polygons. The last case is actually a bit ambiguous. You could alternately consider that there would be 1 water polygon and 2 ground polygons, but For simplicity, I choose to always make it one ground polygon. Fortunately, all of these three cases can be handled by the same algorithm. As we walk counterclockwise around the polygon, we're going to encounter vertices. There will always be a vertex at one of the grid coordinates, and then there will sometimes be a vertex along the edge, depending on if we transition from ground to water. As we encounter these vertices, we simply need to decide if the vertex is going to be added to the ground, to the water, or to both. And as well, we need to decide if we're going to emit a polygon at that time or not. For ground, it's simple. Every time we encounter a ground vertex or one in the edges, then we add it to the polygon, and we emit the polygon after we've completed the circuit. For water, it's only slightly more complicated. Again, every time that we encounter a vertex on a boundary or a water vertex, we add it to the polygon. The thing that's different is that we have to consider the case when there are two water polygons. We're guaranteed that we start on ground. So the first time that we encounter a boundary, we enter the water polygon, and then when we encounter a boundary again, that's when we're exiting the water. All that we need to do is keep account of the number of times that we cross a boundary, and if it's an even number of times, we emit a polygon and reset the polygon. The final thing we need to do is solve for whether the actual crossing happens along the edge. We have the ground heights G0 and G1 at opposite ends of the edge, and we have the water heights W0 and W1. I'll then call the differences in height D0 and D1, and our goal is to solve for the distance t along the edge at which the difference is 0. This gives us that t is d0 over d0 minus d1. Plug that into your parametric equation for the position, and you're done. The last thing to do now is to admire the results. Because of the driver issues that I've been having, I can either have ability to record a video with the new driver or ability to take captures of the timing with the old driver, so you get a still image. And at last, we're at the final step of actually doing the mesh simplification, which was sort of the point of this whole process in the first place. This step is honestly much larger than any of the previous ones on its own. I wasn't really sure how to split it up into smaller pieces though. The main difficulty is just getting simplification to work in the first place, and then other little features like boundary preservation and different levels of simplification for the different MIPS are relatively small, and so it feels a bit silly to make them all into their own separate steps. I'm not going to claim that the simplifier I made is a shining beacon that everybody should copy. It's what I managed to do in a week on the evenings and the weekend when I had free time. It's also specialized for my use case of a terrain mesh, so whenever caveats of things that I just did for expediency or because of the special circumstances, I will try to remember to mention them. The first thing you need for mesh simplification is a way to traverse your mesh. What I mean by this is that given a vertex, you need to be able to find all of the triangles and edges that touch it. Given an edge, you need to be able to find all of the vertices and triangles that touch it. And given a triangle, you need to be able to find all of the vertices and edges that touch it. Given those basic building blocks, you'll be able to get to any part of the mesh that you need information from. As you make any modifications to the mesh, you need to ensure that all of those properties are maintained. I strongly recommend writing a validation function that checks all of the properties that should be true. For example, that all of the vertices referenced by a triangle are valid vertices, etc. This validation can be quite slow and should check every property of everything in the entire mesh, and you should run it in debugging after every collapse if you need to track down errors. Great. So what does updating the mesh actually look like? I simplify the mesh by collapsing edges. What this means is that I calculate the error that would be introduced by collapsing an edge down to a single vertex for every edge on the mesh. In general, the vertex that's the result of an edge collapse could be anywhere, and you would solve to minimize the error that would be introduced. In general, this would involve building a linear system of equations describing the distance of the vertices to the different incident planes, and then solving for the vertex position that minimizes the distance to all of those planes. For my purposes, I just want something quick and dirty. I don't want to bother building or solving linear systems of equations, so instead I just measure the error at the two vertices and choose the one with the lowest error. The resulting mesh will have one less vertex, and then we'll have fewer edges and triangles than it did before. Generally, that will be 2 fewer triangles, but depends on whether the edge was along the boundary of the mesh or not. It can also depend on other things, like if you don't have a nice manifold topology, in which case you might remove 3 or more triangles. Finally, you need to update the errors of the edges that were affected by the collapse. The edges that I've highlighted in green here are directly touching triangles that were modified. They all definitely need updated errors, and also, conveniently, they have to be all touching the resulting vertex, and so they're easy to access. The edges marked in yellow should also technically have updated errors also, as they have triangles that were modified in their neighborhood, but they're a little bit harder to access, and they're going to be less affected, so I don't bother. This is also a quality versus speed trade-off. Updating the errors for edges is the most expensive part of the mesh simplification, and the question is, do you want to run twice as many error calculations per collapse, and is that worth it for the improved quality? This brings us to the question of how are we going to actually update the errors of the edges? We always need to be able to determine which is the edge that would introduce the least error after being collapsed. In order to do this, we need to maintain a priority queue. The type of priority queue that I use is a heap, but if you look at the description of heaps, they're missing some of the update functions that we need, so I need to explain how those work. I store the actual edges in an array, and I don't move their positions in an array so that I can have indices statically reference an edge and be referencing the same edge. Each edge stores the amount of error it would introduce after a collapse as a float. The heap is then just an array of indices into the edge array. Additionally, I'm going to need to be able to update the error of an arbitrary edge. This means each edge additionally needs to know its index in the heap. I'm not going to go into too much detail about how a heap works, and if you don't know, you can look up more details on your own. But the basic idea is that it's a binary tree that's stored in an array, and the index of the array implies the position of that node in the tree. The property that we need to maintain is that the children always have higher error than the parent. In order to maintain this, we'll utilize 2 basic functions, which I call bubble towards root and bubble away from root. The idea is that the entire tree is valid except for perhaps one element, and we will then exchange this element with its parent or child in order to get into a totally valid heap. So the classic update functions are going to still be the same. In order to add a new element to the heap, we'll put it at the end of the heap and then bubble it towards the root. We will always find the lowest error element at the 0th index of the heap. To pop the lowest error, we replace the 0th element with the last element in the heap, and then we bubble that away from the root. The new function that we need is to update the error of an element somewhere arbitrarily in the heap. In order to do that, we modify the error, then we bubble it towards the root, and then bubble it away from the root. And in the end, we have a valid heap again. The functions I show here are written as recursive functions, but I'll note that they could be optimized by tail call recursion to be turned into while loops instead. In my implementation, I didn't actually make a way to delete arbitrary edges. Instead, I just leave the edges in the heap, and they're implicitly invalidated by one of the vertices that they refer to becoming invalidated. So at the time that I try and pop an invalid edge, I then just discard that edge and continue on. However, it would be easy enough to add an edge deletion function, and it would look very much like the pop function, except instead of using index 0, you would pass in the index of the edge that you would like to delete. Additionally, you would need to do a full bubble towards and away from the root for this edge. The pop function is specialized because you're already at the root, so you don't need to bubble towards the root. So at this point, if we know how to calculate the edge errors, I've told you how to always be able to pull off the edge that introduces the least error. I'll give an overview of how we actually calculate those errors now. I won't show the full code because there's a bit of other scaffolding and stuff like that, and it's not really that terribly interesting. But I'll show you the core mathy parts of it and how we can add different components to the error function to achieve the results that we want. The basic idea is that we're going to measure for each edge what would be the error if we selected either of the two end vertices. If we were to collapse that edge, we would choose the end vertex that has the least error, and that's going to represent the error for that entire edge. After collapsing an edge, we need to determine how far the resulting vertex would be from all of the triangles within that edge's neighborhood. In the middle snippet of code, the three vertices of the triangle are given by P0, 1, and 2. The two potential vertex collapse positions are given by pos 0 and 1. The errors 0 and 1 correspond with those positions. If we take a cross product of two of the triangle edges, we get the normal of that triangle, with the length of the normal proportional to the area of the triangle. This works out great because we would actually like the error introduced by a triangle to be proportional to its size. Finally, we'd like to introduce a bias towards collapsing edges that are shorter rather than longer. This will give us a more uniform triangulation. I'll now show the results of using just this part of the error function. We start out with a dense uniform triangulation. When we simplify the mesh, we'll wind up with a mesh that follows the contours of the terrain but has a lot fewer triangles. At the moment, there's nothing that constrains that the vertices need to remain on the boundary of the terrain as a whole, or that the vertices need to respect the tile boundaries in any sort of way. In the top left of this image, you can kind of see that the triangles pull away from the boundary. For each of the vertices, I have bit flags that indicate if the vertex is on an X or a Y tile boundary. When calculating the error of an edge, I then have a precondition that I evaluate before even doing any of the edge error calculations from triangles, and a postcondition that I evaluate afterwards. The precondition says that vertices that are both on a boundary but are on opposite sides of a tile are not allowed to collapse. This is necessary in the case of extremely flat tiles, such as the ocean. The postcondition is what does most of the work, and it says that vertices that are not on a boundary can collapse into vertices that are on a boundary, but that the opposite is not allowed. If I show the result of having no boundary condition and then show the result of enforcing a boundary condition, you can see that now the shape of the tiles is very clear at the resulting mesh. This means that the terrain will not shrink anymore because vertices can't leave the edge of the terrain, and so it's effectively holding the terrain taut like a drum. Having triangles not respect the boundaries was also messing with the culling of the terrain tiles, and so now the terrain culling works perfectly. Lastly, I'd like to maintain a nice crisp boundary between water and ground. Each triangle can either be a ground or a water triangle. I have a very limited set of materials, so I just use a bit mask to represent these. Each edge has a material bit mask that is simply the OR of the two triangles touching that edge. This means that an edge with a bit mask equal to 3 is one that is touching both water and ground. If we were to have a few more materials, we'd have to be a little bit more complicated and count the number of bits, but we have a very special case. I use the convention that z is up, and thus, to preserve the seam, we should have the resulting vertex from a collapse not be too far in the xy plane from the edge. Here, the length of the normal is going to be proportional to the length of the edge. All of our other errors are quadratic, being proportional to area, or the length of the edge squared, and thus we square the error here. And it also gets rid of the sign. If we compare the results from before adding this water to ground boundary preservation versus after, you can see that there are more vertices that are kept along the water boundary. It's a little hard to see in this particular example with just the lines and also not a lot of water boundary, but this also prevents the boundary from pulling away. Now that we've gotten the simplification working, the last thing that we need to do is to generate different resolution meshes for the different MIP levels of our terrain. For each resolution mesh, I pass in a target error to the simplifier, and I collapse edges until that target error is exceeded. For each resolution, I multiply the target error by a factor of 16. As it turns out, this results in a mesh that has approximately half of the number of triangles for each level. I'm not exactly sure why this is, but it makes a sort of intuitive sense. The terms in the triangle error function are proportional to the area of the triangle, so that's a quadratic factor, and then I'm squaring the distance from those triangles, and so that's another quadratic factor. So combining those two quadratic factors, you get a quartic factor, so 2 to the 4th power gives you 16, and that kind of makes sense to me. I wrote a comment that says save the mesh for this MIP level. This is fairly run-of-the-mill code. Basically, I need to compact the vertex indices and reindex the triangles. I also need to determine which tile different triangles belong to. To do this, I determine the average xy coordinate of the triangle and then what tile contains that coordinate. I have a separate array of triangle indices per tile and simply add the triangle to the appropriate array. Here I'll show the results of how the mesh changes as you zoom out. As you can see, it's getting a coarser and coarser mesh the more that you zoom out. Areas that are flat are getting fewer triangles compared to areas that are less flat. For fun, I'll show a wireframe of our classic test mesh of the Iberian Peninsula, and it looks beautiful. And here is what the terrain looks like fully shaded. A side note is that the topographical contour lines that I draw are quite sensitive to the actual heights, and so depending on the simplification, those can move around a little bit. I wasn't very fond of how that looked, and so I changed the pixel shader to read from the height map itself. I didn't put any effort into optimizing the speed of the simplifier really, and the end result is that generating the mesh for the entire world takes about 3¼ minutes. This is acceptable considering that the really final step was that I saved the results to disk so that I don't have to calculate them when just normally playing the game. Now that we've finished, we can look in retrospect at the total performance difference and amount of memory that we've used. At a fairly reasonable zoom level, like the Iberian Peninsula, the amount of time taken in the CPU has barely increased. It's gone from 0.16 milliseconds to 0.23 milliseconds. And in the worst case, when completely zoomed out, seeing the entire world map, the time has now increased to 1 millisecond. I didn't actually think to get the timings of this in the initial state, so I don't know what it was, but it was probably something faster. That said, 1 millisecond in the worst case is just fine, and I don't feel a need to make a hierarchical implementation to reduce the CPU time. In terms of the GPU time, I got pretty close to doubling the speed of rendering the terrain, so nice. One downside is that I do need to store a terrain mesh that is unique for every tile instead of just duplicating one instance. But the cost of that is only 70.5 megabytes for the entire terrain, so that's easily acceptable. And just to cap things off, I'll show a nice little performance capture of rendering the scene. I'll just make a little editorial note here. Unfortunately, the only time I can really record my voice is during the weekend. During the weekdays at nighttime, the baby is asleep and I don't want to disturb him. And there aren't really good sound barriers between parts of the house, so there's a lot of background noise. So I apologize for that.